Good evening and welcome to the Researchers' Night. European Researchers' Night is a public event dedicated to the dissemination of science, and each year it takes place in more than 300 cities across 30 European countries. It aims to bring the public closer to the research in a fun, engaging and educational way. My name is Eugenio Pescimoro and I'm currently a researcher at IDAEA, the Institute of Environmental Assessment and Water Research based in Barcelona. Tonight, I'm going to talk about my current research, which focuses on mixing and dispersion in two-phase saturated porous media. This project is sponsored by the Marie Curie European Fellowship Program. The topic of my research falls into the physics domain, and it is generally regarded as being part of a vast microarea named fluid dynamics, which, as the name suggests, it addresses the motion of fluids. Fluid dynamics, however, is an extremely broad area, since it encompasses all of the non-solid substances that under mechanical stress show similar behaviors. This is because analogous behaviors are typically described by similar physics laws. Some classical applications are the propeller of the ships or the wind turbines. However, the subject of my current investigation is the reciprocal interaction of two fluids flowing through porous materials. When the flow of liquids evolves through tortuous porous domain, the application of the standard fluid dynamic laws become too complicated, thus new simplified versions are introduced. For this reason, the subdomain of today's talk is fluid flow in porous media. Although this study is not driven by a single specific application, its significance lies precisely in the widespread relevance of fluid mixing in porous media, which is an essential phenomenon across a broad range of natural and engineering processes. Indeed, understanding the fundamental principles behind the physics of mixing would allow improvement to a broad range of applications, from carbon capture and storage to hydrogen storage, enhanced oil recovery, including combustion technology and the design of wastewater treatment and biochemical reaction in biological tissues. There are two separate but complementary approaches to the study of mixing and dispersion in porous media. One can perform experiments in the laboratory and measure the results, or it can reproduce the same setup of the experiments by means of dedicated software. While both are needed, the numerical approach to the study of mixing has some advantages over the empirical approach. For example, slow laboratory processes can be speeded up in numerical simulation without losing accuracy, and the cost of a single numerical experiment is negligible compared to the ones performed in the laboratory. However, above all, numerical simulation allow a finer control over the physical properties that would otherwise be difficult to be measured. A porous domain is a solid material with interconnected void spaces, named pores. These pores may be empty, that is, filled with gas, or saturated with liquids. If you water a dry plant pot, the liquid behaves differently from when you water the same plant pot already saturated with water. Thus, for different scenarios, different mathematical models are required. If all the pores are filled with the same liquid, we use the Darcy equation. If the pores are unsaturated, then we tell the software to solve Richard's equation. If the porous material is saturated with two or more fluids, we use Darcy equation with additional parameters. When these equations are solved, the velocity of the flow is known at every point in the domain. This is a useful piece of information that, for example, can be used to predict where a substance dissolved in the liquid will be displaced. The effect of the flow and the porous material on dissolved substances, also known as solids, is typically described by three separate contributions. The first two mechanisms depend on the properties of the solution, and they are typically known as advection and diffusion. Intuitively, you can think of advection as the effect of the stream on a floating log. The log is displaced, but it does not change its shape. Diffusion is related to the molecular agitation, and its effect can be observed when a drop of ink is poured into a glass of water. The dye spreads out until the color of the liquid becomes homogeneous. Dispersion is the result of stirring effect that the rigid porous structure has on the fluid. Now that the porous media terminology has been introduced, it is possible to address the object of the mixing and dispersion in two-phase saturated porous media project. Mixing can be thought as a dilution process, while dispersion is a synonym of spreading. Forget for a second about the porous material and think about when you pour milk into coffee. If you do not stir it, the milk mixes with coffee by simple diffusion, until the concentration of milk becomes homogeneous. If you pour milk into a coffee cup, but then you stir it, the milk is advected with the spoon velocity, while it diffuses in the direction perpendicular to it. It is interesting to notice that the concentration of milk remains more or less steady along the center of the spiral, while coffee mostly mixes with milk in the direction perpendicular to the trajectory of the spoon. The final solution will be the same, but the time and the mechanisms involved are different. Now remember that we are interested in porous materials. If the cup is full of sand saturated with coffee, we no longer need the spoon to stir the milk, since the tortuous path of the pores will have an analogous effect. Being able to understand, mathematically describe, and then predict the mixing and dispersion processes are the main goal of this project. I hope you enjoyed this presentation and thank you for your attention. If you would like to learn more about the topic, feel free to contact me by email. And stay focused on the YouTube channel of Researchers Night and enjoy the rest of the program.